Thank you for watching this episode of From the Field about membrane performance monitoring and filter verification. This is Chris Pudman, and in this on-demand webinar, I will share my insights about creating integrated sampling programs to check process health and product quality. Key takeaways will be an understanding of the issues facing membrane hygiene and what questions can be asked to develop an ongoing plan to monitor performance and cleaning of your filtration systems. I'm Chris Pudman from Statco DSI. We're a sanitary systems integrator with branches all around the country, and I'm based out of the Dallas area. I have 24 years in the food and beverage industry, including 21 years in dairy. My past experience that's relevant to this talk is pilot plant manager for 2 different companies, and where I've had extensive and hands-on experience developing and operating microfiltration, ultra, nanofiltration, and reverse osmosis, as well as being a technical services manager, where I was also responsible for the ongoing performances of multiple filtration processes in multiple facilities. In this webinar, we will cover helpful tips on recognizing filtration inconsistencies and spotting when membrane systems behave inconsistently, capturing data, and really collecting the right data. That's a big one for me personally. Setting performance expectations in terms of defining criteria up front, choosing a sampling method that best fits your needs, and benefiting from the continuous improvements, having it all pay off in the end. So, why do we track filtration performance? It's not just comparing how much uncleanable fouling the membranes have collected since they were new, but it's really asking yourself, is this acting as the package that I need? Achieving fractioning goals, is it creating the output stream that's the right composition for what your plant, what your company needs? And as far as yield, how does the system owner best capture what's happening? Not just to get a daily yield number, but really to find out where improvements on these pretty sizable investments can be made if upgrades are ever justified. So wherever we are fractioning or concentrating, we want to know the current status as well as the behind the scenes diagnostics. To first stay aware of performance, we have to really understand the feed stream and the continuity or lack of on the incoming stream. We all want to expect continuity from the feed stream, but reality is there's changes. And the most glaring example is silo to silo switching, feeding your filtration system. Is it abrupt with reactions happening after the new stream hits? Or are there adjustments that can be made in advance that save a hit or a period of out of spec product? Can you program in the last, say, 1,000 gallons of one silo and blend it in with another? And it goes along with the expectation that some flocculation or sedimentation is going to occur over time in your suspended silos. What can you do to predict for that or make sure agitation or cooling prevents it? Separators will build up in the disc stack over time, and there's adjustments that have to be made that keep your feed stream at target. Otherwise, there'll be drift and continual changes that need to be made. Temperature is a big one. As elements foul, the permeation is slower, so there's more loops around the stage, there's more friction. And we've seen stage coolers right sized, but just not be able to pull out enough heat towards the end of runs. And that really changes the response of your system. As incoming trucks travel through hot climate, as they hold in their tankers, they hold whatever the load is, perhaps milk or cream. There can be a few degrees difference in temperature than the trucks that travel through cooler climate. And when that mass goes into your silos, those will have an effect on hitting your filtration system. Seasonal shifts are a big one. summer versus winter have significant impact on the feed composition, and that affects whether you fortify or you change your volume concentration factor on your filtration system. These are all things to really wrap our heads around what's happening differently on our feed streams so that we can steady out the filtration system downstream. Next, are there microbial changes in the system? And why does this matter if I'm just in charge of the filtration system portion? Well, first, there's a pretty reasonable chance that bacteria can and will collect in the concentrate side of your system, even with all of the cleaning prevention that we do upstream. The most basic side effect of this is blockage or an increase in pressure drop in the first stage. So, fouling, as you know, can snowball and production will drop pretty quickly. Usually, the run will take longer, which means the CIP window gets tighter, gets pinched towards the end of the day, and maybe it barely passes. And really, this is an ongoing effect day to day where foulings are pounded in and it makes the next run even harder. Second, operating temperature. It's really specific to your plant, driven by regulatory or flux rate demands, or really the sensitivity of your streams. But for optimum filtration performance, you could be inside that caution range of around 15 to 50 degrees Celsius for bacteria growth. And it's really helpful to have a sampling system that accounts for this. I'd encourage anyone to examine what your membrane supplier has in terms of autopsy options and be able to pull elements and wrap them in original packaging and send them back so that you can learn more about your elements and what may be happening under the covers. Third, unwanted fermentations can really be happening even if the flux appears pretty strong. There could be something going on where there is organic acid generated and pH could be dropping pretty substantially. That easily affects functionality or flavor or just even the behavior downstream of your products or process streams. Another effect to be aware of is how your filtration system is set up and controlled. To me, a really critical portion is how the startup is done. This is where the water to product transition happens, and it could be the key to a really good 12 or 14 or 16-hour run. Ensuring you do not allow the membranes to flux what they really want to flux when there's no resistance in the beginning at a process baseline pressure and temperature is huge. So when the process stream tries to maintain the flux going from water to product, it'll probably start really hard and then fall back with a lot less permeation than if you kept it on a leash to start with. Setting up the automatic sequences in draining water on incoming tanks or different parts of your system using indicators like inline sensors or hard coded timers in controls programming can really help on optimizing that potential issue of fighting dilutions. And that can happen for hours as you try to get up to a concentration factor if you're concentrating at a high VCF. Knowing what to expect in each stage is important to balancing filtration system health. Adjustments to target flux or stage pressures will allow every stage to complement the other ones and reducing overloaded stages that could die out early and reduce your capacity. Other considerations are potentially changing to larger pore sizes in your latter stages where there's thicker product, most likely. Adding back cow water, RO, permeate as diafiltration techniques can definitely be helpful, or balancing systems with recycle streams. How do I get that meaningful data and make it useful but not overburden the staff at my facility? There's quite a few questions I'd ask you on taking the next steps of getting that meaningful data. So, assembling out of line testing results, it can be highly valuable to align out of line testing with inline instrument needs. What's the plan that can be done for that? Do you pull hourly checks from destination silos along with an inline concentrate? Can you get flagged if a process deviation hits from meters or, say, your inline infrared techniques? Are you getting any artifacts from pulling samples out of spigots that have residue or buildup? Is there time to pull multiple sets of permeate samples, including an end of run set when the baseline is the highest to look for potential breakthroughs across that filtration layer? And where is data stored? Is it a spreadsheet for later use? Is it kept on clipboards? Is there a way to have lab samples tagged so that it meshes with a database of inline process measurements? Do we have sharp enough data to provide healthy and timely triggers and warnings to predict issues in advance so that we can take action? And can there be a laboratory information management system kept up to house all of this really solid data? So, after all these questions on your data collection, now we take a look at the actual rejection of the elements and what can be done to get that calculated and predicted. So you'll likely find that membranes in the same class and the same duty have very similar published rejection values. Now, these are spot or instantaneous rejection values, and they're really on a single pass basis. So, to really know what to expect, you can set up a solid mass balance and calculate what you actually should be getting when you attempt to really concentrate your streams around repetitive loops where there's going to be residence time. So, this slide really shows what the expected protein passage should be as you increase the volume concentration factor at three different levels of published rejection. So you can see, for instance, at 99% rejection and a 3x concentration, I should expect a 0.05% protein to be passing if this is something like skim milk that we are ultrafiltering. If we hit higher concentration factors, like up to 8 times, then it's very normal to expect a 0.075% protein in the permeate. These are all creating solid expectations for you. This is on a batch basis, and my next slide is very similar but flips over to continuous. And instead of percent protein passage in the permeate as the y axis, I show the overall yield in the concentrate stream using three different levels of published rejection. So again, let's take a yield of 98%, the orange curve. If we have a volume concentration factor of 5x, then even though we say we get 98% rejection, we should expect an overall yield of 96% of, say, protein or lactose or whatever we are concentrating in the concentrate stream. Setting up calculations like this based on the manufacturer's data is very useful on giving yourself realistic expectations. In order to cross-check our rejections and keep an eye on this really solid mass balance we're setting up, you need to be able to rely on testing methods. And usually, this is an indirect method based on calibrating from external reference testing. What we need to focus on is that both the reference and the indirect sample measurements must give similar results every day from operator or technician, no matter who is pulling, must be done under similar temperature conditions, since definitely for an indirect method, it will yield different values. Our samples must be very stable and not be subjected to undesired breakdown. And these are things that we will talk through with whoever's doing the reference testing, as well as finding out in advance and discussing the plan of attack with your indirect method, the spectroscopy instrument suppliers. So the sampler considerations, this is what we need to actually pull the sample from the stream, but with a technique that is appropriate for what your plant needs. We need to take a look at the sanitary needs. In the background of this picture, we're pulling a sample of milk from a stream with an aseptic septum. And you may ask yourself, okay, there is a squeegee effect that happens on the needle that keeps all cross contamination out of the sample that we're pulling. That's probably like a sanitary valve in my process where the stem travels through an O-ring and gets a similar squeegee effect. I would say yes, except for in this case, the septum can be used 7 or 12 different times with different squeegee effects. So everyone is brand new. With your sampling valves, there's going to be a back and forth on the same O-ring, and it tends to invite in environmental contamination over time. That's why their O-rings will end up failing and you'll get contamination. So is the sample pulled from part of the process where it's okay to have it go to the floor or have there be some sort of handling contamination? Does it just go to the waste? Is the sample downstream going to be heat treated to where being sanitary doesn't matter as much? Or is there the need that we need to steam sterilize? We have to think about the cleaning procedure for your sampler. Is it something that can flow to the floor? Is it something that you can have moisture collected on the floor? Or does it need to be 100% retained? Do we need to build in an auto purge and have a control system? And is there the expectation that an operator will come in on a late shift during cleaning and take this apart and put it back together? Installation on where are we going to put these? Are we going to need multiple ones, say on a filtration system on different stages? Or can we put caps on and come back and put samplers on when we need? What are we going to need for sterilizing or potentially toggling open and close through a control system? Or can this be something that's a manually acted sampler? And then, of course, we need to make sure that if we need to sample from a line, that it's not 15 feet up in the air and an operator needs to be able to reach it. So if we wanted to go full out, what I show here is a Greek yogurt manufacture process, and all the numbers are areas where you could sample to really get a good idea of how the system is behaving. And this is both from the microbial and a compositional standpoint. When you have a tanker truck that comes in and you go through a process with the fluid all the way to your filler, you'll want to capture several different information points. I believe in aseptic sampling. So what we show here is an aseptic sampling port for all of these different points. Now, they are ones where you may only need composition at certain points, and you may want to get microbial data out of other points, or you can get multiple points of data from each sample. But we start off with unloading a raw tanker. We go into a silo storage where you usually need composition and microbiology. You could separate and concentrate and be able to take a, say, skim or cream stream, split it up, go into an ultrafiltration where you need to know your sample composition and stay aware of bacteriology. You would have a standardization box that we see around number 8 and 9, and feeding into a pasteurizer or hold tubes where it's good to know whether we have knocked out all the bacteria that we are intending to. Downstream of that, sample point 11 and 12 shows our culture addition and our inoculation tank. It's often good to know that we are injecting just the culture that we need and no other cross contamination. And then we have our cooler that happens downstream of our fermentation. This is a good place to be able to understand what the cleaning is doing and if we are making sure we're getting all of our plates clean. Downstream of this, for Greek yogurt manufacturer, we can add flavors or other additions and be able to tell compositionally and microbially if we are hitting our targets just prior to filling. So, in summary, we can put this all together and know that we are setting up expectations and we are examining from start to finish our filtration system. We are taking the data that we get offline and inline, and we are tying it together to be able to understand what we can do to know more about the process and predict when we're going to have failures in advance and be able to set up a plan to where we're operating at a certain standard deviation and be able to tell ourselves if we're getting outside the target areas, getting into warning areas where we need to flag these outliers, set up warnings. And really, it's assembling a sampling plan that we can trust, knowing what we need for our sampling devices, trusting them, and being able to get the data that we can rely on. Please reach out to us with any comments, and we thank you for joining this webinar.